So are you ready?
I'm ready, yeah.
Okay, good. So welcome everyone to another NCTS seminar in algebra geometry. So today we are very happy to have Pierre Bousseau from University of Georgia, and he will talk about KSBA modular spaces of log-Calabi-Yau surfaces. Please.
Okay, so thank you very much for the invitation to speak at this seminar. So indeed, I will talk about some moduli spaces in algebraic geometry, so-called KSBA moduli spaces, for a particular class of varieties, so-called log-Calabi-Yau surfaces. So the first part of my talk will be introductory. I will try to say what are these moduli spaces, what are KSBA moduli spaces, and I will describe what they are in the particular context of toric surfaces, or more generally toric varieties, which was a result known long ago. And so I will review this kind of toric story in the first part of my talk. And in the second part of my talk, I will talk about some new result, which is about KSBA moduli spaces for non-toric log-Calabi-Yau surfaces. And the main result of this talk will be a statement that you can see in the box on this slide, which is a claim that some moduli space, the KSBA moduli space of so-called stable log-Calabi-Yau surfaces, up to a finite cover, is a toric variety. So the main result of this talk will be that some moduli space is a toric variety. And as I will describe in more details later, this was a conjecture by Akin Kiliu. And we prove this statement in some joint work with Valérie Alexeev, and Ilya argues in some paper which is on the archive since a few months. Okay, so let me start at the very beginning. So KSBA moduli spaces are generalizations of Deligne-Mumford moduli space of stable curves. So let me briefly review what those are. So if you fix G and N, some non-negative integers, so that 2G minus 2 plus N is positive, then you can consider all possible, first of all, you could consider all possible smooth genus G curves with N mark points and distinct mark points on this curve, and look for the moduli space of these curves with mark point. And this moduli space in general is not compact, it's not proper, because you can have family of smooth curves degenerating to singular curves with no way to change the central fiber into a smooth curve. And so if you want to produce a proper moduli space of curves, you need to allow singular curves. And one way to do that is the so-called Deligne-Mumford moduli space of stable curves, denoted by MGN bar. And this moduli space is parameterizing a curve C, which is reduced of arithmetic genus G with at worst nodal singularity. So the curve is possibly singular, but the amount of singularity is controlled. You only allow nodal singularity. So analytically, locally, it looks like xy equals 0. And in addition, this curve, you have n distinct smooth points, P1 to Pn. And in addition, this marked curve is supposed to be stable. And there are various ways to phrase the stability condition. One is that the automorphism group of the curve, preserving the mark points, so the automorphism of the curve to itself, mapping mark points to themselves, should be a finite group. And it's possible to show that this condition is equivalent to some ampleness condition for some divisor. The canonical divisor of the curve plus the divisor made of the mark point should be an ample divisor on your curve. Yeah, so you have some positivity of ampleness condition. So here is some, in the middle of this slide, there is a sketch picture of the moduli space and some of the object parameterized by this moduli space, or some nodal curves with mark points. And some remarkable fact about this moduli space is that it's proper. So it's really compact. So if you consider one parameter family of stable curves, let's say over a punctured disk over the complex numbers, then there is essentially a way to put a central fiber, which is itself a stable curve. Okay, so this moduli space is proper. And actually it's a proper Deligne-Mumford stack. So it's almost an algebraic variety. It's an algebraic variety up to this finite group of automorphisms that the curve with mark point could have. And so technically it's a Deligne-Mumford stack. And it is you can show it's of dimension 3G minus 3 plus n. Okay, so this moduli space is one of the most extensively studied moduli space in algebraic geometry, and you should think about it as some compactification of the moduli space of smooth curves with mark point. And the way you produce this compactification is by allowing these slightly singular curves, so-called stable curves. So in this talk, we'll care about generalizations of this moduli space where the curves and the mark points are replaced by some higher dimensional generalization. So instead of having a curve with a mark point, we'll consider pairs YB, where Y is now a projective variety, so not necessarily a curve, and B will now be a Q divisor. So by that, I mean a linear combination of effective divisors with rational coefficients.
So
again,
you
in this
suppose
talk,
that B is effective, so all the coefficients are positive, or?
Yeah, so I was going to say that in this talk, all the coefficients will always be between 0 and 1. So in particular, B will be effective. That's right.
Okay.
So indeed, I will assume B effective. And for such, so you should think of this pair as a generalization of a curve with a bunch of mark points on it, with some higher dimensional generalization of it. And there is some higher generalization of the notion of stable curve. We say that YB is a stable pair if it satisfies two conditions. The first one is the conditions on the singularities of the pair YB. There is a condition that this pair should have so-called semi-log canonical or SLC singularities. So this condition on the singularities is a condition which comes from, let's say, birational geometry or the geometry of the minimal model program. And I will not go into the definition for the purpose of this talk. I will say something more specific, what I will really need at some point. But from the point of view of the general theory, you should think of this definition as a generalization for the case of curves of the fact of singularity that was nodal. So if Y is a curve and if B is a collection of mark points, all with coefficient 1, saying that the curve with its mark points has SLC singularities is exactly the condition that the curve that was nodal singularities, and that the mark point should be distinct and smooth points. Okay, so this SLC is a complicated higher dimensional version of this very simple condition in the case of curves. Okay, so some of the singularities are constrained. And the second condition, which is a stability condition, is one natural generalization of what appeared for curve. You want an ampleness condition. You want the canonical divisor of Y plus the divisor B to be a Q-Cartier divisor. So you want a multiple of it to be Cartier to really correspond to a line bundle. And you want this line bundle to be an ample line bundle. Okay, so this notion of stable pair was introduced by Koller and Scheper-Berendt, first without a divisor, and then by Alexeev in the case of a pair in the 80s. And it has been the work of many people along the years to show that these stable pairs form nice moduli spaces, as nice as a moduli spaces of stable curves. Okay, so in the case of surfaces, it was done by Koller, Scheper-Berendt, and Alexeev, which gives the acronym KSBA for these moduli spaces. And in higher dimensions, it has been the work of many people. And if you want a reference for it, there is some relatively recent book by Koller on higher dimensional varieties, which now presents the theory in a kind of complete form, in complete generality. Okay, so the upshot of this theory is that there are actually nice moduli spaces of these stable pairs. And they're almost as nice as the Lin-Mumford moduli space of curves in the sense that connected components of these moduli spaces are proper Deligne-Mumford stacks. So here the important point is that they are proper. So if you consider families of such stable pairs over punctured curves, then there are ways to extend such families with a central fiber, which is again a stable pair. And it's possible to show that these stable pairs, again, a finite group of automorphisms. So these moduli spaces are almost algebraic varieties. They are Deligne-Mumford stacks because of this finite group of automorphisms. Okay, so from this point of view, these moduli spaces are nice as a moduli space of stable curves. But in other ways, they are much worse. So the moduli space of stable curve, MGN bar, is very nice in a way that I did not describe previously. It is nice in the sense that it is actually smooth as a stack and irreducible. So if I come back here, this moduli space MGN bar has an extra niceness property that it is irreducible of these dimensions, 3g minus 3 plus n, is actually smooth as a stack. And this fact follows from the fact that the deformation theory of nodal curves is extremely simple. So essentially a node can smooth, and that's essentially the only thing which can happen. But in higher dimensions, these singularities which can be present, these semi-log canonical singularities, are much more complicated than nodal singularities and have a very complicated deformation theory. And it follows from that these KSBA moduli spaces are typically singular, and they are not in general irreducible. The connected component could have, for example, several irreducible components. And in general, even describing the geometry of specific irreducible components of this moduli space is something quite difficult. So for the purpose of this talk, I will first describe a specific example of KSBA moduli space in the context of toric varieties. So toric varieties can be described combinatorially. And one possible combinatorial starting point is P, a lattice polytope in Rn, in the n-dimensional real vector space. So by that, P is just a convex hull of finitely many points with integral coordinates in Rn. For example, here I have some example where on the left of the picture, I have a lattice triangle. So I have a triangle which is a convex hull of 3 integral points in the plane. And by a toric geometry, this combinatorial data, this lattice polytope in Rn, defines a polarized projective toric variety of complex dimension n. So maybe I should have said that before. In this talk, I will always work over complex numbers when I talk about complex geometry. And so if I have an n-dimensional, a real n-dimensional polytope, it will define me a complex n-dimensional toric variety. And here is one way to understand the correspondence between the combinatorial data of the polytope and the geometric data of the toric variety. If you have a polytope P inside Rn, you can consider what I denote by C of P, which is a cone over P inside Rn plus 1. So what you can do is consider Rn times R. So you add an extra coordinate, and you place your polytope at the value 1 of this extra coordinate. And then you take the cone over this polytope. You'll get a cone of dimension n plus 1 in the n plus 1 dimensional real vector space. And then you can look at all possible integral points which are contained inside this cone. These integral points form naturally a monoid. If you have 2 of these points in the cone, if you add them up, you get a new integral point inside the cone. And so corresponding to this monoid, there's a monoid algebra, what I denote by C bracket this monoid. So concretely, there is a basis of this algebra given by monomials z to the m, where m are integral points inside this cone. And the product z to the m times z to the m prime is given by z to the m plus m prime, where the addition m plus m prime is the addition of the integral points in the cone. So that way you get a ring, and this ring is naturally graded by the value of this last coordinate I have added. And so I can take the proj of this graded ring, and if I do that, I get a projective variety. And this projective variety is the projective toric variety defined by the polytope P. And actually, because it's proj of a ring, it actually comes with a natural line bundle L of 1, which will be a non-pole line bundle on this toric variety Y. And by construction, the space of sections of this line bundle L on the toric variety Y has a natural basis indexed by the integral points inside the polytope P. So I have this monomial z to the P indexed by integral point in the polytope, and these monomials form a natural basis of the space of section. And finally, as an extra piece of data, so Y is actually a toric variety, which means it naturally contains an open dense complex torus, C star to the n. And the complement of this torus is called the toric boundary divisor. And I will denote by D this toric boundary divisor. It is always an anticanonical divisor for the toric variety. So let me go through an example. So maybe this discussion was a bit general. If I go back to this example on the left, and if I look to this triangle, where every side has lattice length 3, then it's possible to show that the corresponding toric surface, so this thing is a polygon, it has real dimension 2, so it will correspond to a toric surface. The corresponding toric surface is simply the projective plane, P2. And here P2 is viewed as a toric variety. It contains a torus, C star squared. And the complement of C star squared in P2 is a union of 3 lines. So the divisor D, the toric boundary, is a union of 3 lines in P2. And in this example, the line bundle L is, you can argue, the line bundle of 3. And from my general discussion, I was claiming that the space of section of this line bundle should be in correspondence with the integral points of the polytope. And indeed, if you think in terms of homogeneous coordinates on P2, let's say if you think in terms of homogeneous coordinate x0, x1, x2, x0, x1, x2, then the basis of all 3 are all homogeneous polynomials of degree 3 in these homogeneous variables, which will have a basis given by monomials. And these possible monomials are in natural one-to-one correspondence with the integral points in this triangle. For example, in this triangle, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 integral points corresponding to the fact the space of cubic homogeneous polynomials is of dimension 10. Okay, so this thing is a simple example. On the right is a slightly more complicated example. In pink, you see a square, and I could take my polytope P to be this square alone, forget the other part of the triangle, let's just take P to be the pink square. In this case, you can show that the corresponding toric surface is a singular del Peso surface of degree 4. So I will denote by dp4. It is some surface which is singular. It has 4 A1 singularities. And the corresponding line bundle, in this case, you can show is the anticanonical line bundle of this singular del Peso surface. Okay, so the main message from this slide is starting from the polytope. There is a recipe to produce a toric variety Y, which comes with its toric boundary divisor D. In addition, this toric variety is polarized. It comes with a non-pole line bundle L. And Now we'll consider pairs which are essentially built from this data. So we'll consider stable pairs of the following form. Y, so toric variety, projective toric variety Y. And we'll take our divisor to be of the following form. The toric boundary divisor D plus epsilon C, where C is the divisor in the linear system of the line bundle L. And we'll moreover assume that epsilon is very small. So recall that in my general definition of stable pair, I allow divisors with rational coefficients. So it makes sense to have linear combination of divisors with rational coefficients. And here I take a coefficient in front of C, which is epsilon, a very small irrational number. So we'll consider pairs of this form. And it is possible, so why do we take epsilon very small? It's because in this limit, the complicated semi-log canonical singularities conditions for stable pair drastically simplify. You can show that such a pair is stable if and only if the hypersurface C, the divisor C, is torically transverse in the sense that it does not contain any zero-dimensional strata of the toric boundary divisor. So here is a picture where the square is supposed to be a picture of some toric surface, and the boundary of this square is supposed to be a picture of the toric divisor D. And this divisor D has 4 components meeting in 4 points corresponding to the 4 corners of this square. And I've drawn C, a curve in some linear system of some line bundle on my surface. And the claim is as long as this curve does not pass through the corners of the square, then the corresponding pair YD plus epsilon C will be SLC if epsilon is small enough. And then the moduli space we'll consider, what I will learn by MYDL, will be the closure in the KSBA moduli space of the locus of these stable pairs. Okay, so the locus of pairs made of such toric variety with such divisor is not proper because, in general, because this divisor might move in a family and the limit it might go through a corner. And when it goes through a corner, the pair is no longer stable, and so there should be some interesting stable pair limit, which will no longer be a toric variety. We'll describe how it looks in 1 minute. So, but by the general theory of KSBA moduli spaces, there is some limit, there is a closure of this locus of nice pairs. Are there any questions about the definition of this moduli space?
So in this case, if the modular space could be reducible, or in this case, always irreducible?
So here, for the purpose of this talk, I define MYDL as just being the closure of this nice locus. And this nice locus is irreducible. So actually this closure will be irreducible. But you can ask, in the full moduli space of all possible KSBA modules, of all KSBA stable pairs, are there other irreducible components attached to it? And in general, there are other components, other irreducible components which could be attached to it. But for the purpose of this talk, I will only focus on this irreducible component.
I see.
And try to describe it.
Mm-hmm.
So actually, it is known how to describe this irreducible component. It is a result of Vallée Alexeev around 2002, so almost more than 20 years ago. And the claim is that this moduli space, more precisely its normalization, is itself a toric variety. It's a toric variety with fan given by the so-called secondary fan of the polytope P defining this porous toric variety YDL. Okay, so this moduli space is not really mysterious. It's a toric variety. And it has a fan, and this fan is what is called the secondary fan, as introduced by Gelfand, Kapranos, and Levinsky, which is a fan which can be defined combinatorially starting from the polytope P. And I will I will not give the full definitions, but I will say a few words about what is this secondary fan. So this fan, it's a fan in general. If you start with a polytope P inside Rn, this secondary fan lives in a space of much higher dimension. And its cones, these maximal cones, are in natural one-to-one correspondence with particular triangulations of the polytope P, so-called regular triangulations. So here is just an example illustrating how it could look like. So here in this example, my polytope P is a square that you can see in the middle in the plane. And if you look at all possible ways to triangulate this square, there is a way in the right bottom where you subdivide your square into 4 small triangles. And there are these 2 other ways on the top right and on the left where you divide your square into 2 big triangles. And there are all the possible triangulations, and actually there are all the possible regular triangulations of this polytope. And in this example, the secondary fan is actually 2-dimensional, and it is drawn in blue. It is actually the fan of P2, where the 3 cones, the 3 2-dimensional cones correspond to these 3 triangulations. So actually for this toric variety corresponding to this square, which as I mentioned is a singular del Piezzo surface of degree 4, the corresponding secondary fan is a fan of P2. And so the corresponding KSBA moduli space by this result is simply P2, the projective plane. So here it's a coincidence that the moduli space is 2-dimensional, but in general, the KSBA moduli space might be of much higher dimension. So in general, if you consider polytope P, the dimension of the KSBA moduli space and the dimension of the fan will be the number of integral points inside the polytope minus the dimension of the toric variety minus 1. So in this example, I have 1, 2, 3, 4, 5 integral points in this polytope, and I'm talking about toric surfaces. So 5 minus 2 minus 1 is 2, which is why in this example, the moduli space is 2-dimensional and the secondary fan is 2-dimensional. But if your polytope contains many integral points, this fan will be of much higher dimension and the moduli space will be much higher dimensional. So let me try to explain what is the connection between these pictures, these triangulations, and the KSBA moduli space. And first of all, let me explain why this moduli space is toric. So if the moduli space is toric, in particular, it should contain a torus. So there should be a preferred torus inside the moduli space. And here is one way to understand the existence of this torus. So we are considering pairs. So generically, the moduli space is parameterizing pair YD plus epsilon C. And so the pair YD is kind of rigid, it cannot move. The only thing which can move generically in the moduli space is a divisor C. And the divisor C is a divisor in the linear system L. So it has some equation. And the space of section of the line bundle L has a natural basis of monomial Z to the P indexed by the integral point inside this polytope. So the equation of the divisor is something like sum over P, AP, Z to the P. And here the remark is that as long as all the coefficients of this equation are non-zero, as long as they are in C star, you can show that the corresponding divisor will not pass through the 0-dimensional strata of the toric boundary divisor. And so the pair will be KSBA stable. So as long as all the coefficients are non-zero, you have a stable pair. So that way you produce a torus inside your moduli space, which is C star to the power the number of integral points. And actually you need to subtract dimension of Y because there's a torus of this dimension acting of automorphisms you need to subtract. And you need also to subtract -1 because if you rescale the equation, it does not change the divisor. Okay, so, but at least you see why there is a torus inside the moduli space. The existence of this torus is related to the existence of a nice monomial basis for a space of section of the line bundle. Okay, but now the moduli space should be compact, so it should be a compactification of this torus. So geometrically, this toric variety with this divisor can degenerate. Maybe if one of these coefficients goes to 0, the divisor will pass through zero-dimensional strata of the toric boundary. The pair will no longer be stable. So it's need to change to define a stable limit. And the claim is that this picture of triangulations actually are pictures of possible degenerations of our stable pairs. For example, if I come back to this picture of this secondary fan, and if I look at the picture at the bottom where I have subdivided my polytope into 4 triangles, what this picture indicates is that inside the KSBA moduli space, there is a one-parameter family whose general fiber is my irreducible toric variety del Peso surface of degree 4. But in the limit, this toric variety breaks into 4 irreducible components. So the irreducible components are in one-to-one correspondence with the pieces, with the triangles in the triangulation. And each piece itself is toric with polytope given by the triangle in the triangulation. So here are 4 triangles of size 1. So what happened is that this singular surface, del Peso surface of degree 4, degenerate to a union of 4 projective planes, 4 P2s. And the original line bundle breaks into line bundles, which is O of 1 on each of the 4 copies of P2. And the curve C, which is represented in green inside the linear system of L, breaks into 4 irreducible components, which are 4 lines inside the 4 copies of P2. Okay, so this thing is what can happen at like one corner of the moduli space, and at some kind of other boundary strata of the moduli space, we get other degenerations corresponding to various triangulations of the polytope. Okay, so this combinatorics of polyhedral decompositions is some kind of picture of how your toric variety breaks inside this KSBA moduli space.
And can we see the dual graph of the irreducible components from the polytopes? So for instance, in the example of a union of 4 copies of P2.
Yes, so the claim is that the polytope with its decomposition is really the intersection complex of the central fiber. So it's not the dual, it's just the honest intersection complex. So if you want to find the dual, you can draw the dual, and actually we'll do that at some point. But here, these pictures, they are like a direct picture, not dual picture.
Okay, I see. Thank you.
Okay, so here in particular, the claim is that in the boundary of the KSBA moduli space, it's not really mysterious what's happening. The toric variety just breaks into union of toric varieties. And the divisor, torically transverse divisor, breaks into various torically transverse divisor in each of the toric components. Okay, so this thing is a particularly nice example where everything is toric, everything can be understood combinatorially. And for later purpose in this talk, I will mention a way to reformulate how to think about this moduli space in a different way, which will make the relevance of mirror symmetry clear. So at this point, this result, it's a result just entirely in the context of usual classical complex algebraic geometry. But for the purpose of generalizing this result to some non-toric situation, I want to present a dual perspective on this result, and this dual perspective will involve mirror symmetry. And so to do that, let me do the following construction. So from now on, I will assume that YD is a toric surface. So actually the construction here has a version in any dimension, but later at some point I will restrict to surfaces anyway. So let me restrict to surfaces from now on. So if I have YD my toric surface and L some line bundle. So YD is a toric surface, so it's contain a torus C star squared. And I can pick a coordinates X and Y on this torus C star squared. And if I look at some section of my line bundle L, and if I restrict it to this torus, it will become simply a Laurent polynomials in the variable X and Y, denoted by fxy, this polynomial. And the direct connection between this polynomial and the polytope P I was starting with is that P is a Newton polytope of f of xy. So possible monomials which appear, the exponents are exactly the integral points inside this polytope P. And now if I consider this polynomial f of xy, I can look at its vanishing locus on inside C star squared. It's just some restriction of my curve C in the linear system of L. I just restrict it to C star squared. I get some curve I denote by C0. It's a non-compact curve inside C star squared. And then I can use this curve to construct the auxiliary geometry, which will have one more dimension. I can consider the threefold Z, which is defined by the equation uv equal f of xy inside C2, where uv are coordinate on C2 times C star squared, where xy are coordinate on C star squared. So what is this Z? Z is a three-dimensional variety, which is non-compact. And it has a natural map to C star squared. And if you look at the fiber over a point which is not inside the curve C0, you get the equation uv equals something non-zero. And so the fiber is just a copy of C star. So if I draw a real picture, it's some kind of cylinder. But if I look at the fiber over a point in the curve C0, I get the equation uv equal to 0. So I get some like singular affine quadric, some singular cone as represented on this picture. So this Z is a affine fibration in the conic curves over C star squared, which is degenerate over this curve C0. And so the reason to do that is that I'm essentially turning the data of the divisor of the curve C0 into a part of the moduli of a geometry with one more dimension. And in particular, I might want to think, so in the KSBA moduli space, this curve C0 varies, the coefficients of these Laurent polynomials are varying. And by doing that, I'm varying the algebraic or complex structure on this threefold Z. And at least for some motivational purpose, I would like to think of the KSBA moduli space MYDL as some kind of compactification of the modular space of complex structures on this non-compact threefold Z. And actually, this non-compact threefold Z is naturally a Calabi-Yau threefold. It's possible to show that there is a natural volume form, holomorphic volume form, which can be built from the natural symplectic form dx over x wedge dy over y on C star squared. If you wedge that with du over u, you can cook up a holomorphic 3 form on CSZ. Okay, so I really want to think of Z as being a non-compact Calabi-Yau threefold, and MYDL as being a compact version of some kind of modular space of complex structure on Z. It's actually because Z is non-compact, it's a bit tricky to make this statement precise. But at this point, it's only a motivation. It's a motivation to explain the relevance of mirror symmetry. So mirror symmetry is something which should be relevant for Calabi-Yau manifolds, such as Z. And it should be relevant to describe the moduli space of complex structures on the Calabi-Yau manifold. And more precisely, mirror symmetry predicts that the moduli space of complex structures on the Calabi-Yau manifold should be identified with complexified Keller moduli space of a mirror Calabi-Yau threefold, of a mirror Calabi-Yau manifold. So at this point, it's slightly vague. I will be more precise in one moment. But the whole point is to get some kind of dual interpretation of our KSBM moduli space in terms of a dual or mirror geometry. So let me explain in this toric situation what is a mirror geometry. So for toric geometry, mirror symmetry is essentially a combinatorial duality where we replace a polytope picture of a toric variety by a fan picture. So previously, starting with the lattice polytope P, I was using this P to define a polarized toric variety by taking the proj of the graded ring built of integral points in this cone. But starting with this cone, I can do a dual operation. I can use this cone as a fan of a toric variety. So in a concrete way, what it means is take the dual cone and then do the proj construction starting from this dual cone, or more specifically, here I will do the spec construction coming from this dual cone, and I will get a singular toric variety X bar. And because of this cone construction, this cone has a natural projection to a last coordinate, this singular toric variety X bar comes with a natural map to A1. So here is an example. Previously, I was looking to this square, and I was saying that this squared, if I think about this P as a polytope of a toric variety, it's defined a singular del Peso surface of degree 4. But if I view the cone over this polytope as a fan, it is a fan of affine toric variety X bar. And if I have a polyhedral decomposition, for example, a triangulation of this polytope, and if I take the cone over such triangulation, I get another fan, and this other fan will define me another toric variety, which will be naturally a partial resolution of this affine surface X bar. So actually, in this example, it's possible to show that if I take this triangulation of the square into 4 triangles, the corresponding X is the total space of the canonical line bundle over the surface P1 times P1. Okay, so this thing is a non-compact toric Calabi-Yau threefold. And this map from X to X bar is a contraction of the zero section P1 times P1 to a point. If you contract the zero section, you get an affine singular toric threefold, which is X bar. Okay, so here what I'm trying to say is that starting from the same combinatorics as before, but if you interpret this combinatoric in a dual way, instead of producing this polarized toric surface YDL, what we produce is, first of all, some singular affine toric variety X bar, and then possible partial or complete resolution X of this singular guy X bar. And actually, if you take a triangulation as small as possible into triangles as small as possible, you will produce a complete resolutions, which should be actually discrepant resolutions of these singular toric Calabi-Yaus. And you should think about this geometry, this X bar, and all these possible crepant resolutions as being mirrors to this polarized log Calabi-Yau surface YDL, or equivalently to this non-compact Calabi-Yau threefold Z. And here the statement of mirror symmetry should be that this KSBM moduli space MYDL, which, as I argue, should be viewed as a kind of moduli space of complex structure for Z, should be somehow related to a kind of modular space of Keller structure on this mirror geometry X and X bar. And more precisely, it should be a toric variety whose fan is a union of Keller cones of all possible crepant resolutions of X bar. So there is one X bar, which is one affine singular guys. But if you consider different triangulations of your polytope, you get various crepant resolutions. And each of these Crépin resolution will have an F cone, which is some algebraic geometric version of the Kerr cone. And all of these Nef cones fit together inside the essentially relative Picard group. And you can show that they form a nice fan. So this X over X bar are as nice as possible from the point of view of birational geometry. They are example of Morey dream spaces. And so in particular, there are finitely many of such cones, which is combinatorially obvious because there are finitely many triangulations of my polytope. And these cones fit together into a fan. And it's a fact in a toric geometry that this fan is exactly the secondary fan. So this thing is a dual description, an alternative description of the secondary fan. You can think of the secondary fan as a union of Nef cones of these mirror geometries X over X bar. So actually, if you look at toric geometry textbooks, depending on which textbook you look, the secondary fan can be introduced in one point of view or on the other point of view. For example, there is this Cox-Littleshank book on toric geometry, and if you look at this book, it will explain how the secondary fan is related to these Nef cones of this X over X bar. But for example, if you read the Gelfand-Kaplanov-Zelevinsky, they will think of the secondary fan as describing degenerations of these polarized toric surfaces YDL. And the claim is that these two different looking interpretation of the secondary fan is an example of mirror symmetry. And in particular, the toric variety which finds the secondary fan can be viewed either as a moduli space of complex structures for these pairs YDL, or as some kind of complexified Keller moduli space for these Crépin resolutions X over X bar. So I am done with this exposition of the toric story. And now we'll go to the main topic of the talk, which is a non-toric extension. Are there any questions at this point?
Also, just to make sure that all your Crépin
Yes.
resolution here are like just quasi-projective.
Yeah, that's why. So yes. So indeed, it's a technical point. Like I did not explain what regular triangulations really mean. It means that they are defined, they are like the linearity locus of some convex piecewise linear function, which is exactly what guarantees that these Crépin resolution are all quasi-projective.
Okay.
Like, so the map is really projective.
Okay.
Indeed. So yeah, I'm only considering these ones.
Okay, thank you.
Well, yeah, which has this combinatorial translation as triangulations being so-called regular. Okay. So we'll discuss a non-toric extension of this story where toric surfaces YD with an ample line bundle L will be replaced by more general polarized log-Calabi-Yau surfaces. So from now on, Y will be a projective surface. Indeed, Y will be a reduced anti-canonical divisor. And we'll assume that the pair YD are so-called log-canonical singularities. So you will not lose anything for this talk if you assume, for example, that Y is smooth and D is a normal crossing divisor. So, and I will pick L ample line bundle on Y. And we'll make in addition the assumption that the pair YD is maximal, meaning that this anti-canonical divisor is non-empty and admit a zero-dimensional strata. Okay, so in general, this D has several irreducible components which define a stratification of your space, and you want at least one zero-dimensional strata, some kind of. So here, I guess the name maximal comes from the fact that if you look at the dual intersection complex, it is saying that the dual intersection complex of this pair has maximal dimension. So a typical example of such pairs is what we considered before. If I take a projective toric surface and D is a toric boundary divisor, they satisfy all these conditions. But there are many interesting non-toric examples. And here is one way to produce an interesting non-toric example, You could start with a toric example. For example, you could start with P2 with this toric boundary divisor D. And then you could take a point P on the toric boundary. So here the toric boundary is a kind of boundary of this pink triangle. So I take a point on the boundary, but which is not one of the corners, not one of the vertices. And I can blow up this point. Okay, so because I'm not blowing a corner, this blow-up operation is not a toric blow-up, it's a non-toric blow-up. Okay, so I take Y as the blow-up of this point, and I take D to be the strict transform of the toric divisor in the toric surface. That way I produce a pair, and it follows from the way the canonical divisor behave under blow-up that this new pair is still log Calabi-Yau. The boundary is still anti-canonical, but this pair is no longer toric. So for example, the complement of the divisor is no longer isomorphic to C star squared. It's a more complicated thing. And if you think actually topologically, for a toric variety, the interior torus C star squared has a natural torus vibration into torus T2. It has a natural momentum torus vibration over the interior of this triangle with fibers, this tori T2. And if I do this blow-up operation, the new complement of the boundary will have a torus vibration, but now with one singular fiber corresponding to this point I have blown up. And if you blow up many points on the boundary, you'll have many different singular fibers. Okay, so from the topological point of view, you're replacing C star squared that you think as a kind of trivial vibration in T2s, but a vibration containing singular fibers. Here is another way to produce some interesting non-toric example. You could start with P2 and D the toric boundary, which is a union of 3 lines. And you can consider partial smoothing. For example, you can smooth the union of 2 lines into a smooth conic. And now P2, so now Y is still P2, but it's P2 with a non-toric divisor D, which is a union of a line and a smooth conic. And again, if I look at the complement of G and Y, it's not isomorphic to C star squared. So this pair is non-toric. And actually, there is a result of Gross-Aitken-Kill, which says that essentially all possible log Calabi-Yau surfaces with the assumption I made here can be described starting from toric surfaces by doing some of these blow-up operations on the boundary, possibly combined with toric blow-ups. Okay, so there is a way to produce many, many non-toric examples, infinitely non-toric examples, starting from toric examples and doing these kind of blow-up operations. And what we'd like to discuss is a KSBM moduli space for this kind of log Calabi-Yau surfaces. So as previously in the toric situation, I will consider the locus of stable pairs, which are deformation equivalent to pairs of the form YD plus epsilon C, where YD is my log Calabi-Yau surface and C is some curve inside my linear system defined by the Ampere line bundle L. So here I wrote deformation equivalent because unlike the toric situation, so in the toric situation, the pair YD is kind of locally rigid. It does not move in the open part of the moduli space. But these log Calabi-Yau are some kind of local moduli. For example, if you blow up points on the boundary of this toric variety, you have the position of this point that you can move. So these pairs YD have extra moduli by themselves. And so in the open part of this moduli space, you can move the curve C in the linear system, but there are also some moduli of the pair YD, which is something which is not present in the toric situation. And as before, you can argue that the SLC condition, the conditions that you have a stable pair for epsilon small enough, which is the case we'll restrict you, is a case where the curve does not pass through the zero-dimensional strata of D. So as long as you have this condition, you are inside the moduli space, and the full moduli space we consider is a closure in the full KSBM moduli space of the stable pairs of this form. So again, it's not so difficult to argue that this space of like generic stable pairs is actually irreducible. And so the moduli space as defined as being a closure is itself irreducible. And we'll only try to describe these irreducible components. We're not worried about the existence of other irreducible components which might be connected to it. And the main result of this talk, which is in this joint work with Valer Alexeev and Ilya Argus, is the fact that this moduli space of polarized log-Calabi-Yau surfaces, of stable polarized log-Calabi-Yau surfaces, up to a finite cover, it's a toric variety. So the statement is that this moduli space, there is a finite cover of it, which is a toric variety. And what is remarkable in this statement is that there is no toric assumption. So what this moduli space is parameterizing are non-toric log-Calabi-Yau surfaces in general, possibly non-toric log-Calabi-Yau surfaces. So there is no direct toric input, but still the output of the theorem is a claim that this moduli space is essentially a toric variety. So this theorem is a generalization of the previous theorem in the entirely toric setup. And in the entirely toric setup, this previous theorem was maybe not so surprising because everything you start with is toric, so everything you start with is combinatorial. And you could imagine that there is a combinatorial recipe which produces some combinatorial output, and the moduli space will somehow be toric. But for the results that we're proving here, the output is not combinatorial because it's not a priori combinatorial because it's not a priori toric. But still the moduli space is toric. So still, in particular, there should be a fan describing this moduli space. So there should be some combinatorial object coming out from somewhere. And the whole mystery will be what is this somewhere? Where does the combinatoric come from? So this kind of statement was conjectured by Akin-Kil Yu. And actually, the conjecture statement for log-Calabi-Yau pairs of any dimensions. And the main motivation were coming from mirror symmetry. And as I will describe in one moment, the proof that we'll give of the full conjecture in dimension 2 will actually use mirror symmetry in an essential way. Okay, so this is conjecture in any dimension, and the case of log-Calabi-Yau surfaces is the first non-trivial case. If you think about the analog statement in dimension 1, like the log-Calabi-Yau curves are automatically P1 with 2 points, so they're automatically toric. So in dimension 1, the toric case is everything. But starting from dimension 2, as I described here with these many examples, there are many non-toric examples. And it's the first examples where there is something interesting to investigate and to prove. Are there questions about the main statement?
But in the case of a curve, you can also vary this L. So you can put a mark point and more mark point to give obtain a bigger, large, more generalized space.
Yeah, so it's true that you have the freedom to add mark points, but still it will still be a toric example. So in the setup I'm considering, for curve y will always be P1.
Mm-hmm.
D will always be the toric boundary, which will be 2 points with multiplicity 1.
Hmm.
And then I have an extra divisor, so the line bundle can be O of D on P1. And C will be a bunch of D points, all with multiplicities epsilon.
Yes.
And actually, maybe it's something I should have mentioned before. So actually, this is moduli space when epsilon is small enough. Indeed, it is toric. And it's what is called the Lozef-Manin space in the moduli space in the theory of moduli space of curves. In particular, it's different from the Deligne-Mumford compactification, where all the points have multiplicity 1. Here it's a case where 2 points have multiplicity 1 and all the other points have very small multiplicity epsilon. And it's the fact that when all these multiplicities are very small, this moduli space is indeed toric. It's part of this previous toric story I was describing.
I see.
Whereas a moduli space like the Deligne-Mumford moduli space M0 n bar is not toric in general. So you see that this kind of condition on epsilon being very small is a kind of necessary condition to get this toric condition, even in the case of curves.
Thank you.
But yeah, maybe this thing is a good example to keep in mind. In dimension 1, it's just P1, and somehow it's an entirely toric situation. There is no non-toric examples. Okay, so here is the strategy of the proof, and the proof is somehow indirect because okay, we need to prove the Modi space is toric, so we need to come up with a fan. And in the toric situation, the fan is a secondary fan, and there is some combinatorial definition of the secondary fan in terms of these triangulations of the polytope, defining your polarized toric surface. But here we start with a log-Calabi-Yau surface, which is not toric, so there is no obvious analog of triangulations of the polytope. So there is no obvious analog of the secondary fan. So the idea is to use this kind of dual or mirror interpretation of the secondary fan in the toric situation. In the toric situation, we could reinterpret the secondary fan as being the so-called Mori fan, the union of these Neff cones of some mirror geometry. In the toric situation, it was easy to describe the mirror by doing some kind of combinatorial duality, replacing a cone by a dual cone. So here the basic strategy is starting from our log-Calabi-Yau, from our polarized log-Calabi-Yau surface YDL, we'd like to produce a mirror geometry. And our mirror geometry, I will still denote it by x over x bar. It will be x bar it will again be some affine threefold singular in general with so-called canonical singularities. And then we'll study the possible Crépin resolutions, quasi-projective Crépin resolution x over x bar of these canonical singularities. So in the toric situations, x and x bar were toric. In our non-toric situation, n and x bar will be non-toric, and so we need to explain how to construct them. So this thing will be the first main step, the first what I denote here by step 1, and what I call semi-stable mirror. If you want, it's a mirror construction, how to cook up some x over x bar. And once you have this x over x bar, and if you believe that this thing is appropriate mirror, and if you believe that the moduli space you are trying to describe is some kind of complex moduli space, which would have a mirror interpretation in terms of Keller or birational geometry of this mirror, there is a natural candidate for a fan, which is a Mori fan of these Crépin resolutions. So here we're using some fact, which is no longer obvious combinatorially, but which is a birational geometry fact, which is that if you have a Crépin resolution of a canonical singularities, this thing is a relative Mori dream space. It follows some general result in minimal model program. In particular, there are always finitely many such Crépin resolutions. The Neff cones are polyhedral cones. And if you do things properly, they all fit together into a complete fan, which is a so-called Mori fan of these Crépin resolutions. And this Mori fan will be our candidate fan to describe our KSBA moduli space. So if you want to think is the answer to the mystery, where does the fan come from? The fan comes from the birational geometry, the Neff cones of the mirror. But the whole difficulty is to find out what is this mirror. And once you know this mirror and you have this candidate fan, still you need to prove that the toric variety defined by this fan is indeed the KSBA moduli space. And to do that, you essentially need to produce a universal family over this toric variety. And we'll do that by running a mirror construction in the opposite way. Starting from x over x bar, we run a mirror construction. And the output of this mirror construction will be naturally a family of pairs over the toric variety with fan, the Mori fan. And then we need to prove that this family is a family of stable pairs which are in the same deformation class as the original polarized Calabi-Yau YDL we started with. So essentially the whole idea of this proof is to apply mirror symmetry twice. And once you get a universal family, by universal property, you get a map to the moduli space. And at the end of the day, you need to prove that this map is almost an isomorphism. What you can prove is this map is finite and surjective, which is a main statement. So there will be a finite cover of this moduli space, which will be a toric variety. So you should think about these results. So if you think of mirror symmetry as having a B side having to do with complex algebraic geometry and some A side having to do with scalar, symplectic, or birational geometry. Here we're proving a result on the B side. It's about moduli of varieties. And we'll use that by going to the A side, to the Keller or birational geometry side to find out some fan, which will be a union of naive cones. And then we'll need to show that this geometry is indeed the mirror, so we need to apply mirror symmetry twice. So even if our main result is on the B side, we'll make a detour through the A side. So is it correct that the talk is until 10:30, right?
Yes, you have
90
minutes, but you can
In
have
tot-
like 5 or 10 minutes more if you need.
Yeah, I think I will
start
be,
later. Yeah.
I think I will be good with the remaining time to adjust to check.
Anyway, take your time.
Okay, thank you. So I will try to go through some of these steps to give you an idea of what is involved. So the first step, which is supposed to be a mirror construction, will essentially relies on deformation theory. And the point being that existing mirror constructions do not directly apply to this setup. So more precisely, what you want to do is, instead of starting with YDL, you want to consider maximal degeneration of this pair. Essentially, you want to go to a boundary strata of the KSBA moduli space, which is somehow maximal, where YD will break into very small surfaces. And you would like to produce a mirror to this degeneration. So it's a general fact in mirror symmetry that to have a well-defined geometric mirrors, you should consider what's called large complex structure limit or large complex structure degeneration. So here it is what we are doing. You consider a particular degeneration of your log-Calabi-Yau surface, and somehow you want to produce a mirror to that. And there is some technology which is developed to construct mirror to degenerations which are nice properties, which are essentially semi-stable. So with, for example, smooth total space and central fibers which are normal crossings in the total space. So there is this Groth-Siebert intrinsic mirror construction which apply if you take as input such semi-stable degenerations. But the degeneration we care here, which are the kind of families which appear in the KSBA moduli space, are typically not semi-stable. This family of KSBA stemmal pairs, typically they are worse singularities. Typically the total space is not smooth. So we cannot apply this existing construction. We need to find an alternative, and we'll do that through deformation theory. So this thing is the first step. And to do that, we'll use this general result of Groth-Aitken-Kiel saying that, okay, a log-Calabi-Yau surface is non-toric, but it is related to some toric surface by some non-toric blobs. And okay, so you could look at the toric geometry, and in the toric geometry, we know how to produce a mirror combinatorially. So here I draw a picture. So the triangle is supposed to be a toric picture. And here I pick some triangulations of this picture, and I draw a dual picture to this triangulation. And so what is this dual picture in terms of the mirror? So in general, this mirror X over X bar in the toric situation has always a map to A1. It's really a family of surfaces. And the central fiber is a union of toric surfaces. And the dual picture, which is drawn here on the right, It's an intersection complex picture of the central fiber of X, of the toric X, which is mirror to the toric triangle with this particular decomposition. And now if I consider a non-toric log-Calabi-Yau, which is obtained from the toric one by doing one non-toric blob, which on this picture is represented by taking out a white triangle apart from the pink triangles. So concretely, what's happening is that the toric surface corresponding to the triangle degenerate to a union of P2s corresponding to all the triangles in the generation. And then I blow up a point in the boundary of my log-Calabi-Yau surface, and I do that in the degeneration. In the limit, I blow up a point which lives in this particular P2, which is this particular white triangle. So this thing is my particular degeneration on the log-Calabi-Yau side. And on the mirror side, so the mirror we want to produce will produce at some deformation of the toric mirror. And we'll first do it at the level of this central fiber, at the level of this normal crossing surface. So here I draw something, I draw some dashed line on this right picture, and this dashed line is supposed to indicate that some black part of this graph, which was before part of the double locus of a normal crossing surface, is double locus will get smoothed, and I will produce some non-toric geometry as a deformation of this union of toric surfaces. So there is a general way to do that. I will not go into the details of the construction. So there is a combinatorial result due to Engel and Friedman saying that any toric log-Calabi-Yau surface has a nice Symington polytope with central point. So I will not go through the combinatorial meaning of that. Let me just say in algebra geometric terms, there is a particular maximal degeneration of this log-Calabi-Yau surface, which has particularly nice combinatorial properties. And then we can cook up a mirror by starting from a toric mirror, and then by doing some non-toric deformation theory. So here in particular, something which is particularly relevant at the local level is that in this toric mirror, in this toric central fiber, which is a union of toric varieties, some of these toric surfaces have quotient Wahl singularities, which are very particular quotient singularities by a cyclic group acting with weights of a particular form. And it's essential for our story that these very particular singularities have one parameter Q-Gorenstein smoothings. Okay, so there is a whole theory of deformation theory, of local deformation theory of quotient singularities. And here we are using this fact as a kind of local model of what is happening in this construction. So there is some construction involving some deformation theory whose output is a normal crossing surface X0, which is a union of typically non-toric pieces, but each piece is some kind of deformation of a toric piece or union of toric piece. So this X0 is a kind of central fiber of the would-be mirror. And then we produce our mirror by showing the existence of a smoothing of this central fiber. And we prove the existence of this smoothing again by some deformation theory, more precisely some log-smooth deformation theory. And we get some geometry X over delta, where delta is some kind of formal disk. So in general, unlike the toric situation, in the toric situation, X has really a map to A1, some algebraic family over A1. Here, our X is typically only a formal family, but it will be enough for our purposes. If you think complex analytically, you might really think as some kind of just family over some complex analytic disk. And we show that this family has very nice properties. The total space is smooth. The central fiber is reduced normal crossing. X is quasi-projective with trivial canonical class. And actually, it's possible to contract essentially all the compact pieces inside X. So this is a contraction from X to X bar, so that X bar is affine with canonical singularities, and X over X bar is a projective Kerr-Prounce resolution. So essentially what you are producing combinatorially and using deformation, so we do not know how to produce X bar directly. Producing directly an interesting non-toric canonical singularity is difficult. Instead, what we produce is a kind of the Kerr-Prounce resolution. And then we show that you can contract and get a canonical singularity. Okay,
So how do you choose the smoothing, or did you say that there's just one way to smooth the?
Yeah. So actually, for the purpose of what we care about here, the smoothing actually does not really matter.
So you can pick any.
Yeah, here you can pick any, and the answer we'll get for what we do later will not matter.
Okay.
So actually you can put any. So it's true in general there is some kind of moduli space of such smoothing. Like it's not true that there is a particular one parameter family. In general, there is some.
Yeah, parameterized by some H1 or
Yeah, that's right. There might be some kind of moduli, but this moduli will not really matter.
Okay.
Because when we'll do mirror symmetry, this X over X bar will really be on the A side of mirror symmetry. And on the A side, we do not really care about the kind of the complex moduli.
It's a deformation equivalent A side.
Yeah, that's right.
Okay.
Exactly. So, and actually in 1 minute, we'll actually do some enumerative geometry, some Gromov-Witten type curve counting, which has this property of being deformation invariant. So actually the precise details of how you do the smoothing will not really matter.
I see. Thank you.
But indeed, it's a good question, engineer. Okay, so this thing is a kind of a sketch of the first step. We produce this X over X bar, and by general minimal model programs, this X over X bar is a Mori dream space. So there's these finitely many Neff cones. They form a fan, so there's a corresponding toric variety. And we want to show that this toric variety is our KSBA moduli space, so we need to produce a universal family over that. And for that, we'll apply a mirror construction going back. So now we'll start with this X over X bar and try to go back. And now this X over X bar is really nice. It's really semi-stable. So X is smooth and the central fiber is reduced normal crossing. And so it's possible to apply some existing mirror construction. And what we're applying is the intrinsic mirror construction of Gross and Siebert, which is a construction starting with such semi-stable degeneration of Calabi-Yau, produce a mirror. And this mirror is constructed using some enumerative geometry. So here's maybe a nice aspect of this whole story. So the main result of this talk is a result about moduli space of varieties in algebraic geometry. But still the proof, because it goes through the A side of mirror symmetry, the proof will actually use some enumerative geometry and some Gromov-Witten invariance. So even if the statement itself has nothing to do with Gromov-Witten theory, it's a moduli space about classical modular spaces and classical algebraic geometry, the proof will go through Gromov-Witten theory. And the way it works is a mirror of X over X bar that I denote by Yx in the Groth-Siebert construction is defined as a proj of some graded ring. And I will not go into the details of this graded ring, but the key point is that the product in this graded ring is defined in terms of counts of parametric curves, and strictly speaking in terms of so-called log Gromov-Witten invariance of this X over X bar. So this central fiber of X over X bar is a normal crossing surface. And what you want to do is to count rational curves with various contact orders with respect to the double locus of this normal crossing surface. You need to do what is called logarithmic Gromov-Witten theory as developed by Abramovich, Chen, Groth, and Siebert. And it's the main result of Groth and Siebert that there is a way to put these numbers together to cook up some graded algebra. And then you can take the proj of this graded algebra, and this proj is some mirror candidate. And here you can understand at least why this mirror live over the correct base. So this toric variety with fan given by this Mori fan, it has affine charts defined by affine varieties with fan the Neff cone of x over x bar. And the Neff cone of x over x bar is dual to the cone of effective curves in x, or in x over x bar. So actually the local patches on this toric variety are the affine toric variety spec C bracket any x. Like the local functions on this moduli space are monomials of the form t to the beta, where beta are curve classes. And so you can imagine that if you are doing some curve counting problem, and if you weight your curve count by the curve class, if you weight every curve count by t to the beta, where beta is a curve class, what you will get will be naturally function over the space on which the monomials t to the betas are coordinates. So it's kind of clear that whatever you produce lives over the correct space. Modulo some important technical details. If you run the Gros-Hilbert construction in complete generality, you get power series because you get count of curves in every possible curve classes. So you get possibly infinite generating series of Gromov-Witten invariants. And so you might get on only formal mirrors defined over formal power series ring. But here we show that for these x over x bar, which are three-point resolutions of affine varieties, we can control the possible rational curves which appear in such geometry. And we can prove that this mirror is actually convergent in some appropriate sense. It's not only defined on some formal variety, but really on the full algebraic affine toric variety spec C any x. So here what you need to show concretely is that when you take the product of two elements in this graded ring, there are only finitely many curve classes which can contribute to the product. So we need to control the curves which can appear. And this thing uses some parational geometry of curve-point resolutions.
So in this case, your Calabi-Yaos are all still surfaces, not arbitrary dimension.
Yeah, so the Gros-Hilbert construction works in any dimensions.
But
here we have, that's right. So the theorem here that we are writing here only apply to these. So here, the X you should really think is some kind of non-compact threefold, which is a total space of a one-parameter family of surfaces, whose central fiber is a normal crossing surface.
Mm-hmm.
So it will be true that all the curves living into this threefold actually live inside the central fiber. So actually all the curve lives inside this normal crossing surface. So you could describe everything in terms of this normal crossing surface. The only thing you need to remember is the so-called log structure coming from the fact that this normal crossing surface is sitting into a smooth three-dimensional space. If you remember this extra piece of data, you can phrase everything in terms of this normal crossing surface. So I believe there should be a version of this theorem written here. We should be true in more generality, but which is not proven. So actually there is some work by Kiel and Yu, which uses a technically different curve counting series, some non-Archimedean curve counting series. And using this series, they can prove a version of this theorem used in some higher dimensional situations, but under some more restrictive assumptions. So they will need extra assumptions, this x over x bar, which even in dimension 2 are not always satisfied. So definitely there should be a version of this theorem, which is also valid in higher dimensions, but which is not yet established. So the point is running this Gros-Hilbert intrinsic mirror construction, you take the product of a graded algebra, which is in a somehow mysterious way cooked out from curve counting theory, like Gromov-Witten invariants. You get some Y, some family of R varieties. And the claim is that you do not only get a family of varieties, but there is a natural way to produce a family of divisors. And there is a natural way to produce a line bundle because it's Proj of something. And actually, by construction, this line bundle has a natural basis of sections denoted by this theta p, which in the general context of mirror symmetry, Gross and Zibert called theta functions. And you can define a divisor in the linear system of this line bundle by the equation sum of these theta functions equal to 0. So here is a key point of the story I will not have much time to go into. In the toric situation, the line bundles have natural basis of sections given by monomials in terms of the natural coordinates on the torus. Here the claim is that in the non-toric situation, if you have a log-Calabi-Yau surface, there is still a kind of canonical basis of the space of sections. And there are these so-called theta functions. And it's an open question to describe this theta function purely algebrogeometrically, like staying just in terms of the intrinsic geometry of the log-Calabi-Yau pair. Here, the way we'll cook up them will be through these very indirect mirror symmetry construction. So mirror symmetry predicts that on the log-Calabi-Yau surface, if you have ample line bundles, there is a preferred basis of sections, which are some kind of non-toric generalization of toric monomials in the toric situation. And then we prove that these families of varieties with divisors plus epsilon times this divisor in the linear system, we prove that they are really a family of surfaces. And we prove that they are really a family of KSBS stable log-Calabi-Yau surfaces. And we prove that the general fiber is deformation to the original log-Calabi-Yau surface YDL. Okay, so here there are many things to prove because we define this family as a Proj of a ring coming from counting curves. So it's very much unclear what this ring, what the output of this construction looks like. So you need to work to, first of all, prove that the result of this Proj is a family of surfaces. It's a family of log-Calabi-Yau surfaces. You need to prove that the divisors defined by this formula produce stable pairs, which is the hardest part of the whole proof. And at the last, you need to show that whatever you produce is related to what you started with. That the log-Calabi-Yau surfaces you produce are deformation equivalent to the original polarized log-Calabi-Yau surfaces. Okay, so it's a general expectation of mirror symmetry that mirror symmetry is supposed to be an involution. If you have Calabi-Yau and if it has somehow a mirror, the mirror of the mirror should be the variety itself. But to make that precise, it's actually quite difficult, and it really depends on which mirror construction you are using. And here we're using two particular mirror constructions. And if you combine them, it's very much unclear why the mirror of the mirror has anything to do with the original thing. And so we need to prove that. And we prove that using some kind of a trick which relies on complex dimension 2. Essentially, we identify the output of the mirror of the construction at the smooth level, like C-infinity level. We identify the diffeomorphism type of this log-Calabi-Yau surface, and then we use some deep result of Friedman, which only work in complex dimension 2, saying that from this diffeomorphism type, you can recover the algebrogeometric deformation type. So here it's some kind of trick which will not generalize if you try to generalize this argument in a higher dimension, but that we use here. Okay, and very finally, once you produce these kind of families with the right property over this toric variety, then by the universal properties of the KSB moduli space MYDL, you get a classifying map from this toric variety MSEC to this KSB moduli space MYDL. And the final step is to show that this map is surjective, that indeed the family we produce is, for example, it's not a constant family, it's really a universal family, it's really surjective. And in addition, it's finite map, it's almost an isomorphisms. And so we prove the finiteness by showing explicitly that this family is non-constant on particular loci of this toric variety. So here we use some lemma previously used by Hakim Kiliu. And actually, we first prove finiteness, and once you have finiteness, given the fact that both moduli spaces you can argue directly are irreducibles and projective. To get surjectivity, it's enough to show they're the same dimensions, and you can do that by direct counts of dimensions. Okay. So here I have an example, which is actually a very, very simple example, maybe almost trivial looking example. If you consider the pair P2 made of a line in a conic, then in this case, you can check the case. The moduli space is simply a P1. And you can understand the two cones inside P1 in terms of determination of the pair P2 line and conic. You could go through these examples explicitly. But I guess I will just stop there, and thank you for your attention.
Thank you very much for the impressive talk. So are there any questions? Or are there any questions from online? You mentioned about the Gross-Sieber result, like
Yes.
every Calabi-Yau, low Calabi-Yau surface has a toric model. Is it also true in higher dimension, or is still open?
Yeah, so it's not true in higher dimensions. So it is known that there are log Calabi-Yau of dimension 3, which satisfy this definition of log Calabi-Yau like. So it's projective, there is a anti-canonical divisor, it's maximal, there is zero-dimensional strata. But still, so it's known there are explicit examples where such log Calabi-Yau are known to be non-rational. And so in particular, they cannot be birational, so they are not birational to a toric variety, so they cannot be obtained that way from a toric variety.
I see.
So I think these examples are built from, like essentially you can start with one of the non-rational Fano threefold. And for some of them, you can find some anti-canonical divisor, which has a zero-dimensional strata. Or I don't know if you can find it directly. Maybe you need to make a small birational modification to find exactly what you want. But there are some explicit concrete examples showing that there are non-rational log Calabi-Yau varieties starting from dimension 3. So in particular,
yeah, so this is one main obstacle to study the problem in higher dimension.
Yeah, that's right. So it's yes, actually there are many obstacles, but it's definitely one of the obstacles. Yes, indeed. So, but the general picture should still be true. So the kind of general philosophical picture predicted by I Can Kill You and that we are realizing in dimension 2, the picture which is here, this general strategy should still be true. Like there should still be a mirror, which would be some current resolution x over x bar. And the fan should still be the Mori fan of this geometry, but it's all that at every step there will be extra difficulties. Indeed, for the very first step, the main issue is that there is no toric model. You cannot do this. You cannot just reduce to the toric situation and do some deformation theory away from the toric case. You need to do something else for the very first step already.
So for the toric case, is it known for arbitrary dimension or just the surface as well? So
so actually the toric situations is entirely combinatorial and works in any dimension.
Works in any dimension.
Yeah, for the toric story, this is result I was mentioning. Here I really have stated the statement in any dimension. This statement here works in any dimension.
I see.
The point being that here it's like fully combinatorial. It's like going from a cone to a dual cone, and this kind of secondary fan story is understood in arbitrary dimension. So definitely, if you want to go to a higher dimension, you could take various steps. Like you could say first restrict to log Calabi-Yaus which have a toric model, and then try to do a version of what we are doing. But already there are actually many technical blocking steps, like technical blocking steps.
Yeah, even to prove that the double construction is yeah, this is, as you say, at least the argument you use is using the surface and
Yeah, that's right. So I think it's fair to say that currently, if you use this kind of intrinsic, yeah, if you try to do this kind of double mirror symmetry construction where one of the steps is this intrinsic mirror construction, which take as input some enumerative geometry, there is currently no systematic technique to somehow identify what is the output of this construction. In particular, to argue that it's related to the initial one. So here in dimension 2, you can do things, at least you can see at the smooth level what's going on. And then, but in higher dimension, it will be more complicated. So I think there are some ideas in particular cases. Like for example, here we say, if we know that YDL has a toric model, you could try to prove algebrogeometrically that whatever is the output of the double mirror construction has the same toric model. So you can try to identify this toric model in the output of the construction. And which is maybe a possibly alternative way to go in dimension 2, like to avoid this Friedman result. It might be possible, but it will use something else. It will use the existence of a toric model, which again is special to dimension 2. In general, I think there's definitely some missing ideas for how to identify the output of a double mirror construction.
Thank you. Are there more questions? Here's one question.
Do you expect the KSVA moduli or YDL is actually a toric variety?
Yeah, so it's a good question. So in my main statement, I just said there is a finite map from a toric variety. And so there's a question like, is there really a finite map? Is it really necessary? So in the toric situation, the moduli space, or more technically, its normalization is a toric variety directly without having to go to a finite cover. And actually, there are examples where this finite map is really necessary. So I think that in general, this finite cover is really necessary. The moduli space might not be toric itself. You really need to go to this finite cover. And actually, in our paper, it's a bit mysterious what is this finite map. And actually, we are currently writing a follow-up paper in which we'll describe explicitly what is this finite map. So we'll argue that at least on the open part of the moduli space, there's a finite cover with a finite group. And so there is a group which is some kind of monodromy group around, which is trivial in the toric situation, but which can really be non-trivial in the non-toric situation. So this kind of finite cover is really necessary in general.
Thank you.
So for instance, is it still unknown that whether there exists the MYDL which is not rational, for instance?
Yeah, that's right. So I think this thing is some kind of, yeah, I think I don't know the answer to this question.
Okay.
Yeah. So yeah, of course there's a finite map, so it is unirational, but if you ask, is it really rational itself? I don't know.
Are there more questions? If there's no more question, then that sends Pierre again. So thank you very much.
Thanks very much.
So thank you very much for giving the talk at the evening. So it might be late already.
Yeah, it's not too late. It's 10 something p.m.
Okay. So
Thanks.
你要问问题吗? So I think some student wants to ask a question.
Oh, sure.
My question is not related to this talk, but I learned that you have some work on local P2 about its Donaldson-Thomas invariant, and now I'm interested in the Donaldson-Thomas invariant on local P2, so I have some question about it. So what I'm interested in is the cohomology DT invariance on local P2. And so I want to know, is there any result on like degree 0 Donaldson-Thomas invariant on local P2, or any reason result on, is there any the result on cohomological DT on local P2?
Yeah, so definitely it's not related to this talk. So I can only say a few words. So it depends. I guess it will depend which kind of DT invariants do you care about, if they are of rank 1 or rank 0. So definitely the thing I studied the most is if they are rank 0. So sheaves supported entirely on P2. And if you look at the corresponding refined or cohomologically refined DT invariants, then in this case, there are like many results which are known. So for example, I had some work which provides some algorithm to compute these numbers through a so-called scattering diagram. And if you restrict to the sheaves which are supported on curves inside P2, then there are even more results about these numbers. You can show that after some appropriate change of variables, you can organize these numbers into quasi-modular forms, having nice properties. So yeah, there are many known results. Maybe it will be a bit too long to go into that. Maybe it's better if you have a specific question, if you contact me, maybe my email, maybe later.
So I want to make sure. So I know you have some result on local P2. So is it true that because I'm not familiar with scattering diagrams or those things. So is it true that your result says you can determine any DT invariance on local P2 just by some basic invariant, like this kind of result?
Yeah, that's right. So yeah, if you restrict to the one which are really sheaf supported on P2, then yeah, there is a version of this statement. So there will be a very complicated algorithm to reconstruct the numbers, but at least in principle, they can be reconstructed from very simple initial data. So that's true.
Okay. And so what about because the most of the thing I'm most interested in like DTPD correspondence. So I think I'm most interested in the frame quiver. So is it like?
Yeah, that's right. So this thing is some interesting story which is not covered in what I have done, because I say what I've done is only about sheaves supported on P2. But for usual DTPT, you want like ideal sheaves or stable
Yes.
pairs, which are sheaves supported everywhere on local P2. And indeed, what I've done does not apply to these invariants.
Okay.
And indeed, it could be a natural question to, like, how do you incorporate the invariants in whatever I did? And I guess this thing is not done.
Okay. Thank you.
You're welcome.
Okay, so thank you again for accepting our invitation.
Yeah, thank you very much for the invitation.
So hope to see you soon somewhere. So at least yeah, maybe you will go as well. So next summer to Colorado, this summer research institute.
Oh yeah, that's right. Definitely I will be there at least for some time. Yes.
Okay, then at least yeah. So at least I will see you there.
Okay, that sounds great.
Okay, so thank you and take care and see
All right.
you next time. Yeah.
See you.
Bye bye.